Let's just move to the final presentation, where we talk more about pile testing and some of the issues there that you see here on the screen as well, presented by Mohamad Hussein. Mohamad, take it away.
Thank you, Gerald, and hello, everybody. Deep foundations are used to support all types of structures and all types of geotechnical conditions, and to support all kinds of loads, typically very heavy loads. We'll talk about driven piles today, and driven piles are typically made of timber piles, but in more recent years we use steel piles, H piles, pipe piles, pre-stressed concrete piles, or post-tension piles. Now, Gerald, I'm trying to put my picture on the screen. It's not showing. Maybe Valerie can help.
If you just put your webcam on, then everybody can see you as well.
Pardon me?
We can see you. Yep.
We can? Okay, sorry, because I see Gerald's name.
Oh, no, we can see you. You're good.
Very good. A good reference I can suggest for driven piles will be the FHWA manual that can be downloaded for free if you just Google that from FHWA. That's highly recommended. Also, there are other manuals that one can use from the DFI and other organizations related to the design and construction and testing of driven piles. The bottom line is that a pile foundation design generally is not completely finished until the piles are successfully driven to the required depth and load-bearing capacity. For that, we typically use testing and/or quality control by inspection. Testing usually involved or conventionally involves static load testing. However, that has many limitations having to do with cost and time. It takes a lot of time, and sometimes we have limitations of applicability as well. But basically, a static load test would be a foolproof way of establishing the reaction of a pile to applied load. Load test results are as such. But let's try to use the driving of the pile itself in order to extract from it information that we will need to evaluate its load-bearing capacity. So we're going to have a complete system now involving engineering, construction, and inspection to evaluate the pile. Basically, going from the dynamic pile driving resistance during installation to the actual static load-bearing capacity of the pile. So that relationship we usually imply from blows per foot of driving to tons of load-bearing capacity. Of course, that sort of looks like comparing apples and oranges, because blows per foot have no relationship with tons, at least as far as units are concerned. But we're going to try to find that relationship because it's important to do that for a variety of reasons. We know that the relationship typically is the more blow count we have, the more load-bearing capacity the pile will carry, but up to a point where we will approach refusal, where the load bearing would be asymptotic and no more increase in load because we have reached the maximum capacity of the hammer to mobilize resistance. Now, that can be done by computer simulation, by using wave equation analysis procedures, and with that we can come up with a relationship between the driving resistance, that is blow count, and static pile load bearing capacity. But being although a powerful program for simulation, it has limitations simply because it relies on assumptions that one has to employ to do the analysis with. So we start with assumptions, we perform wave equation analyses, and then we come up with a relationship of blow count and capacity, driving criteria if you wish, and also pile driving stresses assessments. Let's not talk about that. Let's move on and talk about measurements and testing. So we will take measurements by dynamic load testing. We will analyze these measurements by signal matching, and then we will refine these measurements and analyses by, again, wave equation analysis perhaps, to come up with a full evaluation of the pile load bearing capacity. We typically do that with a test pile program. So the main goals of a test pile program are to establish production piles length and pile driving criteria. It's also used to check the engineer's design assumptions and the contractor's equipment, means, and methods. So that's a static load test using dead weight. Let's be a little bit smart here, and if we take a small piece of that static load test, dead weight, and if we put it in a guide, raise it high enough and drop it in such a way that the weight of that and its drop height will produce a load on the pile the same as a static load test would have produced. So that's basically the difference between a static load test and a dynamic test. And as it so happened, we didn't even have to do that. That is already being done for us for free. It's called the pile driving hammer. So the pile driving hammer is loading the pile as it is driving it. Now, if we put instruments on it and capture that information, then we will be testing it all at the same time. So the pile driving process itself is a loading process and the testing method at the same time. That is a typical testing of a driven pile. Basically, dynamic testing involves the capture of stress waves inside the pile, what is typically done with a strain gauge and an accelerometer. The strain gauge to test the to get the load, and then the accelerometer to get the motion and the movement of the pile. That is done in accordance to a standard procedure by ASTM D4945. So this is a typical test result from one blow from the gauges at the pile top, on the left side showing the impact, and on the right side showing the reflection from the pile toe. So that is a signature of one hammer blow, one impact, one test result. And as long as the hammer is hitting the pile, we get many of these test results. In this case, this pile was driven 43 feet, and it took 615 blows to drive it. So therefore, we have 615 test results. In this way, organized by however many blows it took to drive the pile each foot of penetration. This data can also be presented in graphical form, so one can see the load-bearing capacity. I'm looking on the right-hand side, load-bearing capacity in blue versus penetration depth, and the blow count in brown versus depth as well. So that's a complete record of this pile showing driving resistance and blow count and static load-bearing capacity versus depth. That information is used to evaluate the hammer performance, the pile driving stresses and integrity, and also the soil resistance and pile static load-bearing capacity. Of course, the performance of the hammer is important because if we're going to relate the blow count to the load-bearing capacity, we have to have a good handle on the performance level of the hammer system. Of course, it can vary by a wide range. That's why it's important to custom make it and measure on each and every job site and project specific information. The assessment of the pile during driving includes the monitoring of pile driving stresses and assessment of structural integrity so that to avoid damage to the piles during driving. Assessment of the soil includes the monitoring of the driving resistance and also the calculation of static load-bearing capacity by means of a signal matching procedures. So therefore, to come up with the pile driving criteria from a test pile program, we start with the testing. Gerald mentioned earlier today the PDA testing of the pile, dynamic load test, then the analysis by signal matching, and finally, by refined wave equation analyses in order to come up with a pile driving criteria that the inspector then uses on site in order to monitor and record the driving of the pile that will be the basis of acceptance. So this is a typical case where the testing was performed to come up with a pile driving criteria. This is a very large concrete pile, and this is a test result in tabular form. So we will go down to a depth of 67 feet where the capacity was reached. They need about 1,000 kips. Then that data is used in the signal matching to extract soil parameters like quake value, elastic compression values, and dynamic damping values. That then gets plugged back into the wave equation for refinement. And from that, we come up with a blow count that is a job specific, project site specific, that now relates the blow count and stroke to the required capacity, in this case, 1,030 kips. This information is then expressed in a pile driving criteria that includes a definition of refusal and also the relationship of hammer blow count and the corresponding stroke that will be required to achieve capacity. There will be other instructions on pile driving criteria, including the thickness of the plywood cushion, for example, and how often it should be replaced and how it should be used. Other instructions may be the performance of the hammer. It should start with lower setting and then increase as the blow count and the resistance increases. And there will be other information in there having to do with driving the pile to a certain depth or stopping the pile at a certain depth. So there will be a decision-making procedure that the inspector will follow during the driving of the pile in the acceptance process of it. And that takes into account many requirements having to do with required minimum tip, minimum penetration depth, required blow count, etc. So there's a procedure to follow there. Now, to apply all that, the pile has to be marked properly, as this pile is beautifully marked. It's driven upright. It looks good. Not always. This pile is driven upside down. Notice the length of the foot on this case between 59 and 60 feet, and the foot between 60 and 61 feet. So obviously the blow count here per foot will not be very meaningful. Here we go from 130 to 135 foot depth, then to 145 foot depth. Looks like they missed 5 feet in their pile length. In this case, we go from 85, 86, 87, 90 feet. So in order for this whole procedure to actually work well, the inspection has to be done properly, and the inspection report have to be done correctly. In this case, the distance between 80 and 85 feet is actually 6¼ feet. This is a pile driving log that the inspector will produce. This is a good looking log. This is a bad looking log. This pile driving log for this particular pile shows that the pile was driven to 28 feet, but there's no blow count at 28 feet. So we don't know what the last blow count was. Remember, blow count is a basis of acceptance. This is a real ugly one. You can't really get much information here. So for that reason, the inspectors go through a process of qualifications through classes that FDOT and others require. And also, they also require specialty equipment to monitor the pile driving inspection and produce automated pile driving logs. So for this whole process to work well, the engineering, construction, and inspection must work together for a successful ending to that. So back to the test pile program and this whole process I have just described, the purpose of which were the production pile length and pile driving criteria. However, this process can be very expensive. To just mobilize to do a test pile program is expensive in itself. It is time consuming because you have to do a test pile program, and then you have to come up with production pile length. You have to make the piles, bring them, and so on. So time consuming. It might not even be warranted in certain cases, and in others it could be completely ineffective. That is why, alternatively, some projects now drive production piles without test piles and blow count criteria, but with 100% dynamic pile testing. 100% dynamic pile testing has many benefits, including optimization of construction efficiency and economy. It's actually cheaper, as it was found, to do 100% testing than to do a test pile program in many cases. And I think in many situations, they show that it's the only way to do that. Furthermore, it increases engineering reliability, which means that now with all of that data available from each and every blow of each and every pile, the engineering reliability is increased, which would allow for the use of a lower factor of safety, therefore better utilization of the piles, or if you like in the LRFD, a higher fee factor of design. So there are many benefits and advantages to the use of 100% testing. These pictures in the background there I'm showing are from projects that either started out as 100% testing by design or got turned into 100% testing after the test pile procedure was started on each project. However, there's a flip side to that, which is a major issue that requires that the production pile length must be done and must be known ahead of time without the benefit of a test pile program. So the engineer must assign production pile length to the project really without much prior information from that site. And this is a case where the you see a soil boring in there, and clearly the piles will drive down to about elevation minus 100, and they will hit refusal. That's what happened. You see the blow count going down and hitting refusal, the pile capacity with nothing, and then hits refusal at exactly what's expected. So that would be a case where really a test pile program would not be very effective or useful because, well, the length of the pile is pretty much known here. And the installation of the piles can be instrumented in order to control stresses and avoid damage. So therefore, a test pile program in this case would not be warranted or very effective. However, there are cases where it wouldn't be, as would be the case here. The same kind of similar situation, you would think that the piles will drive down to elevation 0 in this case from plus 70. So you'd expect 70-foot long piles based on the soil boring, clearly. However, in actuality, H piles, HP 14 by 89, driven with a diesel hammer, the piles did not even see that layer. At that depth, at 0 elevation, the blow counts were in the 15 blows per foot, and the capacity of the piles were very low. Another case, this is concrete piles now. You'd expect the piles to go down to their depth, but in fact, the piles went down 20 feet deeper, even though the end value showed to be a refusal at about 75 feet penetration. At 75 feet penetration, there was none of that, and the piles had to be gone. So that is a challenge that the engineer would have to weigh, and the contractor would have to weigh, and the applicability of 100% testing, but because the production pile lengths have to be known beforehand. So this is a project where actually a design build project where the contractor and the engineer team decided to utilize both. They utilized the probe, they call probe piles, or let's say test piles, along the alignment of this bridge project, and then utilize 100% testing. And the contractor said in this case that it's the best pile driving job he's ever done because he has the benefits of both the test pile program information and the 100% testing that helped in the scheduling and in the cost of it. So with that, I know I had 25 minutes, so I stuck to the time. And with that, happy pile driving to everybody. And I'm ready to take any questions, Gerald, if anybody has any.
Thank you, Mohamad. And not only